Hi everyone. So I'm Tobias. I'm also with Akamai, and I have dabbled with images for a while being a little more than 3 years now. I've also created a talk about that, and I've been giving that talk for more than 2 years now, for the simple fact that I've created a couple of tools that I thought would be helpful, and I learned a lot about images, and I thought images are a big problem, so I want to spread the knowledge that I've acquired about this, because when I started, I had the feeling that since 1992, nothing major has changed in image optimization. So I thought, maybe I'm going to talk about it and tell people that actually things under the hood have improved, and I want to show you what and how. So, when I got started with that whole thing, with the whole shenanigans of image optimization, I had a customer that wanted to launch a website, and I was so happy to have them, because they were like, we want to have a performance budget. And so I applauded them. It was the first customer that proactively, without me telling them, wanted a performance budget for their site. So good. But then they sent the usual crap over, PSD files and images that were 5 megabytes big. I was like, I can't put that online. I have to compress those images. So I compressed those images. And of course, these image compressions caused compression artifacts. But being a performance engineer I was like, I'm not going to tell the customer that, because the small image is going to load faster. So let's just see if they're going to be okay with the small images. And of course, they weren't. They hated it. They were a design-focused customer, so they saw the compression artifacts within the first 1.5 seconds of seeing the demo website. And then they said, there are compression artifacts in the image, we're not taking that. Damn. And that was my job being crushed. So I was really in a bad mood and thought, I have to get rid of these compression artifacts, but I need small images. How do I do it? And I figured out a way, and I'm going to talk about that today. The problem I've been facing back then has now a name. The name is hero images, because in the last 1.5 years, this design with large images at the top has become so predominant that they now called hero images. So this is a web design term that you will encounter when you look at web design trends in the modern age. And the hero images have caused such a big problem that they also in the web performance community now have a name, namely the hero image delay, HID, H-I-D, coined by Steve Souders in his blog post. The reason being because these hero images are almost certainly the largest image on a website. These images are also the slowest to load. So as web performance engineers, these are images that create a huge problem for us. So what can we do? To answer the question, what can we do? We first have to look at where's the biggest problem. These are diagrams from the October 1st run of HTTP archive. So as recent as it gets, because the latest run of by the end of October was broken for some reason. And as you can see, images make up 1,400 kilobytes of that entire website. And the statistics are for the Alexa top 1,000. So this is an average. That translates into like 64% of all the data that is shipped over the wire to make a website is image data. That's big. In terms of HTTP requests, that comes up to anything between 20 and 40 HTTP requests in general. It's really, really a lot of HTTP requests just for images. And that also translates into a strong correlation with page load time. Sorry, I can't walk, and I always need to walk when I'm nervous. So page load time means when the page is completely loaded and JavaScript events can fire. But pay attention that page load time does not mean user experience. You can have a very, very well-performing or subjectively well-performing website where the onload event is at 12 seconds or later. That's not correlated. So the perceived performance is not page load time, but page load time is an important metric for us. And seeing that 1.4 megabytes of image data have an impact on page load time is kind of obvious. So this is what Steve graphed here for us. And in terms of file types, we also should ask ourselves, is there a file type that's more predominant than the others, so we should optimize that first? And yes, there is. JPEGs. JPEGs make up almost half of all the image byte size that we ship over the wire, because JPEGs are that predominant. In terms of HTTP requests, again, that's like anything between 10 and 30 HTTP requests just for JPEGs. And in terms of transfer size, this is something between 200 and 400K on an Alexa top 1,000 average. So it's a lot. It's a lot of JPEG data. So the problem here is users hate to wait. So we should fight the JPEG first. Let's smash the JPEG's head in with a baseball bat. That would be cool. The problem with images and JPEGs especially is also because we now, as you all are currently holding them in your hands, mobile devices. So we have the rise of the mobile web. And mobile web wants images just as fast as the desktop web wanted just on mobile connections, which is even a bigger problem. And especially if you have roaming data like I have right now, 100 megabytes of roaming data doesn't buy you a lot of website loads if every website is 1.4 megabytes of images. That's a problem. So we have to reduce image file size. And also with responsive images, we are now shipping several resolutions of images depending on how you implement responsive images, which is also a cause for a stronger need for image optimization. So now I've come up with a lot of problems. We have responsive images, we have JPEGs, blah, 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 blah. What can we do? What, as curious monkeys, can we do? Because the truth is, we can't really get rid of images. Remember 1992, where, you know, the web was like these text files? That was fun, but it wasn't really emotionally engaging. The thing with images is they are emotionally engaging. When you see an image on the internet, your brain is triggered in so many different regions that can't even be described in a two-dimensional image like that. So a plain text website is quite boring to the human brain, while an image immediately triggers so many reactions to us. It's an emotional response. It makes us buy stuff or donate money or whatever. It does an awesome kind of stuff. Images are super important for conversions because they trigger the human brain so well. They convey emotions. Images convey emotions like no other medium. So we can't go back to the sweet world of 1992 and go like, I'm going to create a plain text website. That's not going to fly. Not in 2015 anyway. So let's look at the tools available for us to solve that problem. First tool is not a tool. That's fun. The first tool is think about how you load images. Async all the things. So most of the websites I've encountered as a web performance consultant are still loading their images synchronously. As we've seen, we've got anything between 20 and 60 HTTP requests just for images. And if you consider that all these images are loaded, you might ask yourself, are all of these images actually viewed by the user? And the truth is, of course, no. If you look at engagement maps with your websites, you see that you have a lot of drop-off to the bottom. In most websites, depends on how you design them. Of course, there are exceptions to this. But there is a big chance that a huge amount of your users is downloading these images but never seeing them. So why are you pestering their bandwidth with that? Why are you decreasing your website's performance by forcing these images to load if your users are not viewing them? So think about asynchronous loading and only load synchronous images for the above the fold. There's a battle, I think this is like 10 years old by now, if there with the mobile web there is still such a thing as above the fold or not. There are a couple of web designers who will tell you there is no above the fold anymore. This is not the paper print. Above the fold is dead. But if you extrapolate what above the fold means for web design, it means if you encompass your 95% of mobile users, that you can be certain that they don't have a screen size larger than 1,200 something pixels vertical. So why load any images that are below that? So there are good JavaScript libraries that make it easy for you to load images asynchronously. I personally like Lazy Sizes by Alexander Farkas. It's brilliant. And you can just tag images below the fold as asynchronous loading. The nice thing is also it enables you to think about what is the super important image you need to load synchronously. So it's a kind of the same thing as we have with CSS. When we want to optimize a website, we think of a term that's called critical CSS. So which CSS is super critical to render above the fold, the famous Ilya Grigoric 1000 milliseconds time to glass. So we think about critical CSS, and I want you to think about critical images. Which small part of the images that you ship on your website are so critical that they need to load synchronously. All the other stuff, tag them as asynchronous loading. Another technique is this. Oh wow, that's blurry. The reason for that being blurry is this. It's called low-quality image placeholder. This is a technique created by Guy Pojami, one of the awesome people at Akamai, now freelance again. He came up with that in 2013, I think. And oh yeah, sorry, I see people taking notes. That's good. The entire slide deck is up on SpeakerDeck already. That's speakerdeck.com/tbaldorf. You can find the entire slide deck with all the URLs there. Back to business. Low-quality image placeholders are a very, very fine technique to get around the problem of slow loading images. What they do is you create something like this, a super blurry preview of the image that is a couple of 100 bytes big, and then when a high resolution version of the image is loaded, it gets replaced, gets switched out. The nice thing about that is, first of all, when the website is rendered, the DOM has something to work with because there's a small image that will have the same resolution as the later to come high resolution image. So the page can be laid out by the browser. Good. Also, your users get a impression, a very early impression of what might be in that image, and they get a taste for the colors inside the image, etc. So for the human brain, there's already a response. And then when the high resolution image comes in, they can view the details. So this is nothing that's supposed to stay on for 10 seconds. This is something that's supposed to stay on for a couple of 100 milliseconds to give the users a good impression of an image loading, and then the high resolution image can replace that. So Facebook has experimented with this year. This is the Facebook developer blog, code.facebook.com, and they found out how to ship low quality image placeholders in 200 bytes or less, which is freaking brilliant. 200 bytes for a low quality image placeholder is just brilliant. So I encourage you to read that blog post. I'm currently working on an update for that technique. It's not public, so I don't have code to demo, but I hope I will, maybe by the summer next year, because I just had a kid and that eats up a lot of time. But yeah, aside from that, I'm working on that, and I'm calling it SKIP, because LKIP stands for low quality image placeholder. This one is going to be called scalable quality image placeholder. As you all might have guessed by now, it's about vector. So I'm going to be doing the same thing, just that the image preview is not going to be done in a raster image, but in a vector with blurry lines. So I'm going to create a outline with SVG and going to blur that all. And that will hopefully enable me to also drill down the low quality image placeholder in SVG to a couple of 100 bytes, which is going to be smooth. That's at least the idea. Also, the blurriness inside SVG will scale much better than a fake blurriness with a raster image. At least that's the plan. Let's see if that works out. Okay, so lots of workarounds. But those are not really the image encoders I want to work with, right? There are ways to deal with the fact that we have to ship images, but they're not really the nitty-gritty of image compression. So I'm going to go into that now. So what do we have? JPEG, as we've seen. We have JPEG all over the place. The funny browsers you see here are Netscape Navigator 2 and Mosaic browser, because they were the first browsers that supported JPEG in 1995 and 1996 respectively. That was really cool, because when Mark Andreessen created a Mosaic browser with GIF support, people were like, wow, awesome, I can finally share images over the internet, not just plain text. Remember the plain text websites? But then they realized, well, this just has 256 different colors in GIF, and my cat content just doesn't look good on that. So I need something better. And the nice thing is that the JPEG working group had been open sourcing the JPEG license, and JPEG was available back then. So when browser vendors found out that humans have a need to share actual photographs and not just 256 colors with GIF, they took JPEG to implement that. They also built in BMP, so bitmap support. And I actually, when I remember that, in my youth, I actually saw websites that shipped bitmap images. So you had like a website that was 10 kilobytes large, because that was how big the HTML was back then. But then you have an image of 5 megabytes that came in the next 20 minutes because bitmap. So that sucked. So we needed something that's better, that compresses well. And the answer back then in 1995, 1996 was JPEG. So let's look at how we can make JPEG better. While Gavin was giving his talk, I did something really nasty. I came up here and took a photo. Hold on. That's the photo. Oh yeah, it's a little emptier than now because people were coming in. But thank you for smiling, because that made the photo so nice to pick. So yeah, I took a photo of you. I hope you don't mind, because I like to demo, stuff with people being here. So that photo is huge, and I took that from my iPhone. And because I want to put it on the internet, and I hope that flickering goes away, I created a smaller version of it so we can work with it tonight. And the version I created with the GIMP, because I want to demo something that is quite common. A guy taking a photo of on his cell phone and then wanting to publish this photo on the internet. And a common workflow for that, if I'm not doing that 500 times per day, is using something like Photoshop or the GIMP, right? So I just opened that photo, made it a little smaller because let's assume my website has a width of 768 pixels, and I compressed it. And I used the Save for Web plugin, as everybody should do, of course. So this is GIMP's result of the image with Save for Web and a quality of, well, go away, a quality of 85. And let's see how big that is. Oh, wrong folder. What am I doing? No. Sorry. Here we go. Embarrassing. Okay. So the image is the iPhone photo, 1.5 megs. We're not going to ship that. And then this is the source image. And remember, quality 85 created by the GIMP. The JPEG is progressive. Does everybody know what progressive means? I want to see heads going like this. Good. Progressive JPEG renders in different layers. Awesome. Yeah, I think that's it. And all you have to know is that the GIMP bases his Save for Web plugin on libjpeg, which is the standard JPEG library on the internet. Libjpeg is constantly being updated, but yeah, it's the most common thing we have for working with JPEG. So it's nothing fancy, and we are at 68 kilobytes. That's okay, but not specifically great, right? So that's the source image. Okay. So now we know what normal JPEG encoder like libjpeg with a little enhancement by GIMP would do with this image. 68K. All right. So, like I said, JPEG is was created in 1992 and put into the internet in 1995, 1996. So you might assume there must be something better by now, right? And so did other companies. One of them being Google. And my usual question, who has heard of Webp? Wow, that's really low. Usually it's like, everybody has heard of Webp. Amazing. So in 2010, Google came up with the idea to create a new image format because they said, well, all the image formats on the web suck. They load slowly. We want to have websites load faster, so we need a better image format. So they created Webp. They also created WebM, the image video thing. So Webp was supposed to be a very smart, modern image format. It is supposed to replace PNG8, PNG24, GIF, and JPEG. So you have different bit depths, so 8-bit and 24-bit. You have full alpha transparency channel, you have animation support, and you have lossy encoding like you have with JPEG, all in one image format. So Google thought, one file format to smite them all, to make all the needs of all the web image formats go away and unite them. That was the idea. So they had a little bit of a licensing issue at the beginning, but they figured that out quite quickly. And Webp got a lot of fame, got a lot of love between 2010 and 2012. Since then, and of course, other companies thought, we can't just let Google dictate policy here. We need to create our own format. Who of you reads XKCD, the funny little comic? Cool. Okay, who of you remembers that funny comic about, oh no, 12 different standards, we have to work on it? That's exactly what happened. So yeah, another company came up with, oh no, we need to solve it all once and for all. And that company was Microsoft. Microsoft thought we can't let Google dictate policy, and we have just acquired that funny company that was working on something for HDR images, so we're going to fork that, splice that out into something we're going to call Jpeg XR for extended range. And this file format will then be able to deal with different bit depth, which is important for HDR, and will compress better. That was the idea. And then they botched licensing issue for open source really big time. So Jpeg XR was dead before it was even out. So that's kind of sad. Nobody really cared about Jpeg XR. So let's look at these two contenders again for JPEG, right? Let's look how well they might do. Webp has a funny problem. You need a binary to work with Webp because Webp, although being open source, isn't implemented in a lot of tools. There are plugins, but meh. So on the command line, you work with Webp like this. C Webp for compress Webp. I'm using, again, the quality switch for 85. I'm giving it the source JPEG as an input and say Webp quality 85 output. Nothing fancy. Let's see how well that done. How well that did. And 48. Huge savings, right? That's from 68 to 48. That's pretty good. It's 20 kilobytes. That's really, really good. I like Webp. Well, there's a problem with Webp, however, and that is, can I type? No, can I use? Can I use Webp? Oh, hold on, I'm going to get that up for you a little. Can I use Webp? And the answer is no. Oh, well, only on Chrome. Google Chrome is the only browser, or basically the Blink engine is the only engine that supports Webp. There is no other browser engine that has the intent to implement Webp. So now you could go like, I'm going to polyfill Webp for all the other browsers. It's fun, yeah. Have a JavaScript engine decode binary data. That's great. That's a brilliant. No, don't. Don't do that. So support for Webp is only available where Google had control. So you might ask yourself, why the hell then on Opera? Because Opera switched from their engine to Blink, like what, 1 year ago? 1.5 years ago? Yeah. So that's why they also now have support for Webp. That's the only reason. So working with Webp is kind of difficult. You would have to target Chrome dedicatedly. Or you would have to find a workaround to ship Webp to other browsers. Not a good idea, as I just mentioned. Another problem you'll face with Webp is, I would never do that, but there are people out there apparently who save images they see on websites to their local disk. I don't know why, but some people just enjoy collecting. Humans are, harvesters. So when they see a funny cat content picture, they right-click and save it. And then you'll figure out if it's Webp, I can't open the damn thing. It's on my disk, I can't open it. What am I doing with it? If you right-click on Webp on any operating system, the only tool that's available to open Webp is Chrome. It's ridiculous. So it's really bad. People don't like that. They expected an image to be open in their Photoshop or GIMP or whatever, and without any plugins, that wouldn't fly. Another thing is Webp achieves its amazing compression by dumping a little bit of color information. And some people, especially regarding faces, have the impression that human flesh color in Webp looks plasticky. And that's bad, because humans react really, really bad to the uncanny valley effect. You know, when something might just look like a human face, but there's something off with it, like with a Borg, resistance is futile. So humans resist really, really, they resist that thing. They think like, oh, that's a bad face. Or something is wrong here. They have an allergic reaction to the uncanny valley effect. And Webp has the bad luck that it kind of triggers that. So people don't react well to Webp. Facebook, as you've seen with the LKIP thing, they are using Jpeg because they switched to Webp and away from Webp for these very reasons. Their users hated it, although it was loading faster, apparently. So that's an issue. So maybe Webp is not the answer. That was 2010 to 2012. In 2013, a funny guy who studied history, I think, which I really love about him, because I also studied history. I'm like, history nerds are good for something. Came up with the idea of maybe we can use Jpeg with a modern Jpeg encoder that is smarter and still get proper file size like Webp does. And he did a study with something that didn't have a name back then, and showed that his new tool might actually achieve that. So small file size, less visual impact, less compression artifacts, and blowing Webp and Jpeg Xr out of the water. Almost a year later, that tool in 2014 was then labeled Mods JPEG, because this guy was working at Mozilla. So that's Mozilla's JPEG implementation. At the back, by the way, you can see a red Godzilla fighting Google Chrome UFOs. I love that. Such a cool image. So they ran that study in November 2013 and November 2014. Got a lot of bad press after the first run, but were able to disprove all the criticism in the following year. And then Mods JPEG was accepted as a very, very good tool. By now, companies like Facebook dump a couple of tens of thousands of dollars into Mods JPEG development because, yeah, the major Fortune 500 companies have figured out that keeping with that tool from 1992, JPEG, is a good thing, because all the browsers still have JPEG support built in. Why create a new format? All right, let me show you how well Mods JPEG does. So what I've done here, mods.jpg, because mods.jpg wants to be a replacement for libjpeg, you would use cjpeg on the command line. The thing is, cjpeg is currently used on my operating system by libjpeg because I wanted to use both in parallel, so I symlinked to mods.jpg here. So don't be confused when you install mods.jpg that mods.jpg as a command on the command line will not be available to you. You will have to symlink to it. So this is mods.jpg, and I'm creating a progressive, blah, blah, you know, with quality 8.5, blah, blah, like we've discussed before. Let's press enter and see how it does. Shoop. And let's see the file size results. So, 67 kilobytes, that's awful. What the hell, mods.jpg, you're supposed to be good. That's not good, that's not good at all. That kind of sucks. The truth is, mods.jpg is brilliant, but it's highly conservative about ruining images. So when you don't tweak mods.jpg to be more aggressive about compression, it tries to not ruin your image, because as we've discussed at the beginning, compression artifacts suck. And the mods.jpg crew wants to make sure that none of their images, the output images, has compression artifacts. So they're very, very, very conservative about this. Now comes the interesting part where I got busy. If you want to find out how much an image has changed between an input image and an output image, there's lots of ways to do this. There are good ways and bad ways. Let me cut it short for you. I'm going to tell you the good way. The human eye is quite difficult to nail down on how it views things. But the algorithms being developed in the last 10 years have gotten closer and closer. There's been such a thing as the peak signal to noise ratio to compare images. It has been replaced by the similarity index or the structural similarity index. There are forks of that created 2012 that are even closer to the human eye. That are called CWSSM, so complex wavelengths analysis for structural similarity index. Don't try to remember that. I was looking for a tool that was simple enough to use, and there is a guy who is basically the guru in image compression, and he also had a need to use the structural similarity index. And his tool is called dissimilarity index. That's DSSM. And the guy is called Cornel Lisinski. Who has heard of Cornel Lisinski? Ah, okay, cool. At least a couple. Who is using ImageOptim on the Mac? Okay, so I think you're the only diff in this group. Cornel Lisinski has created that. So Cornel Lisinski rocks. He creates image optimization tools that are free and are very, very well performing. And one of the tools that he needs to do that magic work is this. It's open source, it's on GitHub. And what it does is it expresses the difference of an image, hopefully very close to how the human eye would perceive these differences, in a simple number. A simple number we can programmatically use. And to make it, I forgot one small detail. The similarity index can only be calculated from PNG images because you need a lossless data source for that. So I've created a wrapper called dsimcompare, which just creates two PNGs from two JPEGs on the fly in RAM and then feeds that to the similarity index, so I don't have to create the PNGs manually because I'm lazy. And this is how it would look. We've got a number here. We have a number. Oh, I should show you something beforehand so you can trust that tool. So we're going to compare one image to the same image. That's going to be fun. So I've now compared an image A to image A. And obviously, the dissimilarity is 0.00000. For the source compared to the mods.jpg result, we have a dissimilarity of the, what is that? That's 2%, that's 0.04%. So there is a visual difference of 0.04% between the mods.jpg output and the source JPEG. And that 0.04% is expressed in that 1 kilobyte. That's it. So as you can see, mods.jpg hasn't changed the input image a lot. However, you might ask yourself now, if you are awake, you might ask yourself, how much can I change an image until the human eye detects the difference? Good question. The answer is we don't really know, but there has been some research. And the research that we have had was done by Radware last year by Kent Alstead and Tammy Everts. and they've created a fictionary image format called perfect image that could cover all the bases, and they compared that perfect image, so something that would load instantly, would have all the color, blah, 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 and they compared that to all the image formats out there, and then try to measure with a, what was the company's name? Neurostrata? Yeah, I think Neurostrata. So a neurological research facility, how the human brain perceives images and how they react to the differences inside these images. So they actually had people hooked up with all these little plugs to their brain and measured that. And the output result that is found in their white paper they created for that last year is 1.5%. That's the answer, the approximate answer. 1.5% is the sweet spot. At least that's the one study that we have that tells us that. If you are into neurological research and you have some budget, rerun that study, please. I need a I need a source that can rely on that. So when I learned about that we have this 1.5% gap that we might make use of, I thought, why not enhance mods.jpg's compression so that it will always output a file that is almost 1.5% different, so that we create maximum file size savings without botching the image. And the result is Jpeg DSIM. As you've maybe remembered, Jpeg stands for compressed JPEG, and DSIM is the dissimilarity tool. And that is a very simple script available on GitHub open source BSD license versions 3.0, which is a simple binary search, actually. You know how binary search works? Cool. So it starts off with a JPEG quality of 80 for mods.jpg, so it runs mods.jpg under the hood, and finds out how much visual difference is in the initial run. So when mods.jpg ran with a quality setting of 80, how much difference does that incur? And if it finds out the difference was too big, then it tries to up the quality because it wants to make sure that we stay within that 1.5% margin. If the if the visual difference was not enough, it'll lower the quality to get a smaller file. So that thing basically automates the entire process of finding the sweet spot for image optimization with mods.jpg. It looks something like this. Jpeg DSIM, and I'm using the mods.jpg compression algorithm on the source image. Now, as you can see, it takes a couple of seconds because it's a binary search, so it runs the image compression not once, but up to x times, x being anything up to 100. But usually, because it's, oh God, it's like walking down a base tree, so a binary tree. So most of the runs are done after 6 or 7 splices. So, how did we do with Jpeg DSIM? Oh, hold on. Get that up there. Source JPEG, Jpeg DSIM. 36 kilobytes. That's pretty sweet. Come on, I want to see smiling faces or something. Reaction. Yay! That's really cool. I mean, you know, we've got JPEG here, full browser support, and we downed that sucker to 36K. That's even smaller than the bloody Webp. And that's without the plastic face thingy that happens when you use a Webp. That's pretty good, right? Right? Good. Yeah, sure. Oh yeah, the 1.5%. That's, yeah, so it would be 0.015 because the structural similarity index uses a range from 0 to 1, and the values after the dot, after the comma, are 2-digit percentages, single-digit percentages, and then comma after the percentage. So 1.5% or 0.015. That's it. Yeah. Oh yeah. You wanted to see the images to be sure that it still looks okay. Yeah. So that's the source image. Okay. Oh yeah. We can make an interesting experiment that's going to come in handy in a minute. Where would we expect compression artifacts if I compress that image strongly? Where would I see compression artifacts first? The spot on the right. Why? Why? Gradient. Yes. Gradients are horrible in JPEG. That's good. Anything else? Edges? Yeah. Oh yeah, the text. Yeah, text is also really bad. Actually, I think it's you currently adjusting the camera, and I think you might also create a compression artifact in there, because you're a high contrast area within a gradient. That's probably the worst that a JPEG can ever encounter. So thanks for standing up when I took that shot. Okay, now let's look at the mods JPEG quality. Oh, maybe I can put them side by side, but I don't have a lot of screen space on the projector. Hold on. Zuck. And no. Yes. So that at least there's a little. So this is. Yeah. Oh, well now I'm getting the not actual size. So let's go to actual size. That's actual size versus actual size. So we don't have compression artifacts from the zooming of Mac. So when I'm pretty sure we can't see that on the projector, but here are a couple of compression artifacts in the source image already with quality 85. And they are not really more visibly stronger on the mods JPEG version. But now let's look at the one that was really, really small, because that's probably the one that's going to have the most. That will be this one. And let's go to actual size so we don't botch it. And there are more compression artifacts visible. So we have actually lost visual quality. We have lost visual quality of 1.5% measurable, but you, as human viewers of that image, can see the difference already. And this is where another tool comes in that I'm going to demo you. So Jpeg Dsym, awesome tool to find the smallest quality setting that is still acceptable, but it does create a visual difference. And now I'm going to demo a tool that might help with that problem too. Chip, chip, chip. So that was Jpeg Dsym. As I told you at the beginning, I got bashed by my customer because my JPEGs also had compression artifacts. So I had to go back and ask myself, how can I avoid them? And I asked myself the same question I've been asking right now: where would I get compression artifacts? Gradients, high contrast corners, text, that's it. So I thought maybe I should detect these things and not compress these areas as strongly as other areas. The thing is, JPEG isn't built to create several qualities within the same image. So I kind of worked around that. At first, I used all-directional Sobel edge detection algorithm to detect all the edges inside an image. And then when I hit an edge, an edge was highlighted in white. When I detected an edge inside an image, I said, don't compress that part of the image as strongly as the other parts. And I did that by splicing the image into tiles, so small pieces of the same size. The JPEG encoder is helpful in this regard because JPEG also uses tiles when compressing an image. It doesn't compress every single pixel, it compresses blocks of 8 by 8. So I was using the same approach. I cut my image into 8 by 8 blocks, and for each and every block, for example, for the input image we've seen, this is 2,500 blocks. For each and every of these 2,500 blocks, I detect, is there a corner in there or not? If there's a corner in there, be careful. If there's no corner in there, compress the hell out of it. That was the idea in 2012-13. Then I realized, however, because of the uncanny valley effect, human faces, for example, they would create corners around the eyes, the nose, the mouth, but I would get compression artifacts on the forehead, the chin, the cheekbones, everything that's a little smoother, where the Sobel edge detection algorithm would not detect corners. But I want a face to look pristine because humans are good at detecting errors in faces. So I needed something better than Sobel. And my answer was saliency mappers. Saliency mappers are algorithms that make computers be able to understand contents of an image. They are there so that CCTV cameras out there can identify that I just went to McDonald's. Oh, sorry, privacy nerd. Or they are good to hone in drones to kill people. That's also horrible. My goodness, I can't think of anything good. They're good to identify if a cat is visible inside an image. Okay? So saliency algorithms are good to identify content within an image. They are created to be highly performant because with cameras, for example, we need to process 24 to 60 frames per second. and they need to highlight areas within an image to a computer that those areas the areas that need to be interesting. Because if the computer was trying to process the entire image, it would have a problem. It needs to have a cue, like look at that part of the image, look at that part of the image. And so I researched university papers on saliency mappers and came up with, oh, I should have stayed in there, and came up with one, ta-da, the maximum symmetric surround saliency algorithm created by a guy in Switzerland for his university research. So he's a doctorate, and he just dumped his Visual Studio files on the internet without any licensing. I was like, hey, dude, this is an awesome saliency mapper. Can I just, open source that? And he was like, sure, do whatever the hell you want with it. So I was like, okay, BSD license 3.0 it is. And I had the good fortune to work with smart people in my team, people much, much smarter than me. And those people, Jed, should be here, I hope, soon, ported that sucker from Visual Studio to proper C++. And we open sourced that on GitHub. And its output looks something like this. Ta-da! See how fast that was? Really, really fast. Very cool. And check. This is a black and white representation of the input image that we've seen. Let me show you the input image again so you can memorize it. Right? People in rows looking in front, looking to the screen. And the black and white map. And what has the saliency mapper detected? It detected the red shirt is very interesting. Your face too, by the way, very cool. A couple of other faces also very interesting. Here's a couple of faces that get areas that are deemed less interesting, probably because they have very smooth gradients. As you can also see, very good feature of MSSS, it detected that bloody gradient we had. Because JPEG would have problems with compressing that, so it highlighted it as an area we should take care of. So now what I could do is with that map, I can iterate over the image from left top to bottom right in 8x8 blocks and find out, are you black or are you white? Are you black or are you white? Are you black or are you white? 5,200 times. And then whenever I encounter a block that has a certain percentage of white pixels in them, I'm going to deem this tile interesting and will not compress it strongly. All the other tiles that are mostly black or entirely black can be compressed very strongly, and they might not create a compression artifact. That's the idea. And the tool to automate, because that's a pain in the ass, the tool to automate this is adapt. So, oh yeah, let me demo adapt. And adapt will now do this 5,200 times. And as you can probably imagine, this is going to take a while. So let's look at it working, because otherwise this won't be very interesting to you. Here, 5,200 tiles in my temp directory, because I'm hoping that Mac stores that in RAM and not on disk. And yeah, they're getting processed and processed and processed. That is going to take a while. So an important lesson here is don't judge all JPEG encoders by their real-time capability. I've seen too many engineering blogs going on with that JPEG encoder is not fast enough for real-time. And I've also seen NVIDIA salespeople running around saying that for image compression you need huge NVIDIA GPU clusters to compress your images in real time. Unless you are, I don't know, steering a drone across the world, you really don't need real time. You really don't. You can create async pipelines. When a user uploads an image, show them the uncompressed image for their session. That's totally fine, because it's just the user who uploaded that. Then put that uncompressed image into an optimization pipeline server that you've set up somewhere, and let that image be crunched later. To buy yourself and your servers some time so that they can optimize that image for you, and then you can replace the uncompressed version with the compressed version in any given amount of time that you want. But don't throw out the idea of image optimization, because most JPEG encoders are not real-time capable. That's a bad idea. I've seen that too many times. Don't do that. So rather think of the benefits that a JPEG encoder can buy you or the JPEG encoder cannot buy you. So adapt is very, very good in buying you images with very, very few compression artifacts. Jpeg Dsym, on the other hand, is very, very good in finding a sweet spot for one quality setting for an entire image, but it goes for the aggressive small file size. So you kind of have to ask yourself, what do I need? For a hero image, I'd suggest go with adapt, because you want no compression artifacts in this. If you are creating 250 by 250 thumbnails because of a blog post preview, use Jpeg Dsym. Nobody cares if there's a little compression artifact in that small of an image. So, oh yeah, sorry, there's a question? So the tiles actually get compressed by mods JPEG depending on each and every content, which means the quality gets adapted per tile. So both Huffman table optimizations, trellis table optimizations, etc. are per tile. So you end up with 5,200 tiles. Some of them are compressed with high quality, some of them are compressed with low quality, and then I'm using ImageMagick to reassemble the entire array of 5,200 tiles, and I'm running a Huffman table optimization on the entire image for the simple fact that depending on what kind of an image I have, I might not have a multiple of 8. That gets a bit nerdy now. JPEG encoders have a problem with it. Now I'm getting nerdy, right? JPEG encoders have a little problem, and that is if you're not working with an image that is a multiple of 8, the JPEG encoder will have to buffer that extra stuff, the extra pixels, to the next multiple of 8. They will have to add padding to be able to process the last tiles to the right and the last tiles in the last row. So we are encountering padding with cutting images apart and reassembling them with adapt. And that padding is worth nothing because there's no image information there. So after adapt has reassembled the image, I'm running a Huffman table optimization again to drop all that unnecessary padding bytes without losing quality, because Huffman table optimization is a lossless process. Wow, okay, that was... Yes. Yeah, it's weird, isn't it? Oh, you mean our different quantization matrices embedded in each JPEG? No. There's just one global one afterwards. Yes. Yeah. Yeah, of course. Otherwise, that image would be huge. Yes. No, it's not. So afterwards, there's just one quantization table. No, I'm using... Oh, wow, you're asking very good questions. I think he does image processing. So I'm using Jpeg Rescan, which brute forces the quantization tables. So yeah, okay, I can talk about that too while adapt is running. So there are lossless optimizations to JPEG. JPEG is always deemed a lossy format, so it loses information with every compression. But there are a couple of optimizations you can run which don't lose information. And those are Huffman table and trellis table optimizations. And there is a tool that has been out forever, Jpeg Tran, which is using some smart math to optimize these matrices. So shall I really get into that? Yeah. Okay, so a matrix in JPEG is built up like there's one big number at the beginning, and then there are lots and lots of small numbers that multiply or divide this number to come up with to make the information stored inside a JPEG more compressible. That's the basic idea. So you have like a, I don't know the English terms for that, a multiplicand, yeah, multiplier, yeah, you have a multiplier, and these informations are stored in matrices. And oh, it's done, cool. So I'm hurrying up now. So that's how. So Jpeg Tran tries to find a formula that is more efficient at expressing these numbers, making these numbers smaller, making the byte size smaller without losing information. Jpeg Rescan is a Perl script created by one of the developers for the H.264 codec that just brute forces Jpeg Tran. So it doesn't run once, it runs up to 100 times and tries to find the most optimal formula to divide these numbers even further to create a smaller file size. So it's like a brute force script for lossless optimization. That's Jpeg Rescan. And that's the last step in adapt. So adapt has run, and we've got an image that looks like that. Can we see major compression artifacts? I can't. That's really cool. So let's see how big it is. Source adapt compress. 52K. That is pretty good because we had 68K to begin with. Mods JPEG without any enhancement, 67. We've got Webp at 48. And now with adapt, we are almost at Webp's quality setting, Webp's file size almost, but we have a much, much better quality. I can even demo that in terms of numbers, so you don't just have to believe me, I can demo that. So we're going to compare source to CJPEG DSIM for funsies. That should be a very high number, because like we said, 1.5% should be about, and we can see we're at 1.4749% difference. Now let's see how well adapt did. That's cool. Oh, yes, I'm so glad. Sometimes that doesn't work out, depending on what's in. So adapt has created a visual difference of 0.8%. That's pretty sweet. So I might actually be able to drop some more quality in the future run and create an image that still has no visual artifacts, but is even smaller. So with adapt, I have actually proven, Jed always claims that I fixed JPEG, which is kind of cool. I'm really proud when he does that. So with adapt, I've kind of proven that JPEG, when exposed to smarter encoders, is able to create file sizes equal to Webp or Jpeg XR, but without all the negative sides. So that's really, really cool about adapt. Bad side is adapt is a bash script that is just a proof of concept. If any of you has free time or is friends with a C developer, please take this tool and implement it in C native, because then this run of adapt will take about 0.1 second. That would be brilliant. I can't code C, so I can't really do that. But this is something that needs doing. Cornell is porting adapt to Mods JPEG, but he's also doing that in his free time. So I'm not expecting this to land for anything earlier than Mods JPEG version 4.0. Currently we're at 3.1. So it's going to take a while. All right, onward. I still have more stuff to do, to tell. So we've talked about adapting JPEG quality for all kinds of shenanigans, right? Compression artifacts because of high contrast areas, blah, 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 blah. How about adapting JPEG quality dependent on network performance? Cool. Oh yeah, cool is the right direction, yes. So this is a bay in Hawaii somewhere. I didn't take that photo, sadly I wasn't in Hawaii yet. And when you pay close attention, you can see compression artifacts and less and less and less compression artifacts. The technique here is called adaptive image compression. These are 10 different steps visible to alter the JPEG quality in that example image. And the integer which we use to adapt that JPEG quality is the network performance. So we are measuring the round trip time between, say, my mobile device and a server. And if the round trip time is good, I'm shipping a big image with high resolution and less artifacts. If the round trip time is terrible, say I'm roaming on my way to Paris in the Thalys in the countryside, which I did today, and I just have the glorious 2G thingy in my upper right corner, then I will be able to still read a news article and see the photo, although it has some compression artifacts with that technique. It's really, really cool. There are service providers who are offering that service, but you can also implement that yourself. You can use, Gareth already hinted at that, the navigation timing API can be used to detect the round trip time and then adapt the JPEG quality. So you can actually build that yourself. It's cool. It's really, really cool. Love it. Okay, so there are a lot of things you can do to JPEG. Some of them are naughty, some of them are cool. There are things you can't really do to JPEG native. One of the things that Webp still has over JPEG is alpha transparency. There are ways around that too. There is a tool that is called Zorro SVG, which I think is a really cool name, and it does the following. First question. Who has heard of the clown car technique by a stale veil? Two, okay, so I have to explain that. Before Joaf Weiss saved all the web developer community because he implemented responsive images natively in all the modern browsers, we had a problem with responsive images. And there were a lot of solutions being attempted to fix the problem of shipping different sizes of an image for different kinds of devices. Estelle Veil had the brilliant idea, Estelle, do I say her name right? Estelle Veil had the brilliant idea to embed raster images, aka JPEG, inside an SVG container, because you could create media query breakpoints in SVG and then switch out the image dependent on how big the screen currently is. It's a really, really nasty, cool hack. I love it. It's brilliant. Zorro SVG does the same thing, basically. You have a SVG container, but inside is a raster image, the JPEG, this beautiful bottle of beer. Sorry, that was the example image. And with it, inside the SVG comes an alpha transparency mask. If you ever have worked with Photoshop or GIMP, you're probably familiar with masking, where you can overlay certain areas. That's the same process. You have an alpha transparency mask, a mask that gives a meta information about certain parts of the image. This mask then gets subtracted from the raster image by an SVG filter and creates full alpha transparency. That's really, really cool, because now we have full alpha transparency with a lossy JPEG format under the hood. Saves a lot of file size too. Much more than shipping PNG24. Please don't ship PNG24. I've seen too many e-commerce stores where you need some sort of image on the shopping cart and they use PNG24. The last thing I saw was 400 kilobytes per image because of that. That was awful. So don't do that. There is a way to use PNG8 with full alpha transparency. PNG8 can theoretically only carry 256 colors, just like GIF. However, again, Cornel Lisinski, I should probably start donating that guy some money. Cornel Lisinski improved the Floyd-Steinberg dithering algorithm for colors, which enables you to have high-quality photos in PNG8. So even if you take a photo of a gradient, we've discussed gradients look bad when compressing them strongly, but even with gradients, if you use Cornell's algorithm, these gradients will look quite well. And you can ship a full alpha channel with PNG8 too. So you can also use PNG8 plus full alpha if you use Cornell's tool. It's called PNG Quant 2. If you don't want to do that, you can use that technique. So wrap a SVG container around a JPEG and then subtract an alpha transparency mask from the JPEG. Nasty hack. Problem with that, of course, is you need SVG support. So Android 2.0 is out. So if your customer base is in Africa right now, you can't use that. So there's good news still, and that is, and I'm coming to the final part of my talks now. So there is a light in our future. There's a bright light in our future, and that is the Jpeg Xd format. And unlike Jpeg Xr, don't confuse that. Jpeg Xd is being developed by the proper JPEG working group, so it's official. It's not a company hack to get more metadata into images. It will enhance the JPEG format by several bit depths, just like Webp, so 8-bit, 16-bit, 24-bit. It will give JPEG the ability to do full alpha transparency, and it will also enable JPEG to have proper lossless encoding, which JPEG arguably doesn't really have right now. Now you might say, well, but don't we have the same problem like with Webp, browser support? Another format, really, Tobias? You've been talking for 45 minutes, and you're going to say the solution is another format, really? Bad, Tobias. Now, the good thing about Jpeg Xd is Jpeg Xd is going to be backwards compatible. And that's a really mind-blowing part. So every bloody browser since 1995 will be able to display an image, even if it's Jpeg Xd. And the simple reason being that Jpeg Xd is based upon shipping a normal JPEG as the base image inside. So you will have something like progressive enhancement inside an image format. So old legacy browsers will be able to display a normal JPEG. Modern browsers, which will be able to support Jpeg Xd, will render a normal JPEG, but enhanced by alpha transparency, different bit depths, blah, 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 blah. So this is how they're going to do it, and it's really, really cool. It's currently being developed, and they are, of course, launching a lot of studies. One of them is already showing that Jpeg Xd will also outperform all the existing image formats. You're having Jpeg Xr there, and one of the outputs from the H.265, I think, and my fiend, I hate that thing, Jpeg 2000. Huh? Sorry? Apple? Apple. Sorry, Apple. Ah, yes. Apple is the only bloody company that supports that. So, because I have always gotten that question, what about JPEG 2000? Because JPEG 2000 is, for some reason, memorized fondly by people. Because they thought, oh, well, it does arithmetic encoding, so it must be performing better than anything. But the problem is, oh, okay, sorry, you can't see that in the back. Hold on, run it again. JPEG 2000 is only supported by anything controlled by Apple. So the native WebKit stuff and iOS. That's the only supporting browser. And that's bad. Just the same problem we had. Bloody hell, we're turning yellow again. The same problem we had with Webp. So that's not good. That's no good. Jpeg Xd, however, will blow all of that out of the water because it will even outperform JPEG 2000. So that's going to be really, really nice. If you are really nerdy about image optimization, you may sign up for that mailing list. This is where the Jpeg Xd development is currently taking place and where you get announcements about current features. You can also access the demo software. It's on the Jpeg Working Group website publicly, but you can access the most recent implementation if you sign up there. You can discuss JPEG development there. It's really, really cool. You will have to argue your case why you want to be on that group, so I don't accept anybody for no reason. But if you're really, really nerdy about image optimization, you might get in and discuss that. It's really cool. Yeah, so as you can see, it's run by a university. The reason being somebody will have to have the time to do this. So okay, let's sum the whole show up. Takeaways. Use mods JPEG right now because it's so cool. And depending on your use case, enhance it with CJPEG DSIM or adapt, right? Adapt, hero image, CJPEG DSIM, smaller images that you need to ship quickly. Also, load them asynchronously and follow the Jpeg Xd development because when it comes out, it will make all our current image formats redundant. You will never have to deal with PNG8, PNG24, or Webp or Jpeg XR ever again. So once Jpeg Xd has gotten proper browser support, and it will, I promise you, this one will blow them all out of the water and it's going to be brilliant. So thank you very much. And yeah, that's me. By the way, if you have any questions in the following days, feel free to hit me up on Twitter. I do reply to these things. All right, any questions? No, I don't think so. That's the only thing it doesn't do, as far as I know. Everybody's hungry? Good, good, good.